Hi everyone. In this video, I want to tell you about the concept of the work done by a force. Um, this is basically how much a force can help or hinder a movement and how we can measure that. And we're going to use it as one of the applications of the tools of integration that we have been learning. But to start with, there are going to be no integrals. I just want to explain the concept of work. So if you've already taken a physics class, you're probably familiar with the concept. But let's think of this situation. Uh, we have a certain body, okay? Um, think of a box or just any particle that's going to move from point A to point B. And along this movement, there's a force being applied to this body, okay? And we're going to make some assumptions on this force. First, so I'm denoting the force by F with a little arrow on top, is this vector here. Um, and we're going to assume that the force is constant. So throughout the whole movement, this force being applied to the body is not changing. So think maybe you're pushing this box with exactly the same strength and towards the same direction throughout the movement. And the force has to point either in the same direction of the movement or in the opposite direction, right? So it's either totally going to help or going to hinder. So, for example, we should not consider for this uh, discussion, we should not consider forces like that, for example, where it's not exactly along the same direction. Right? So this is not good for us. So the units of force, they're usually measured in Newton. A Newton is a kilogram times meter divided by second squared. If you think of Newton's second law, it says that force is equal to mass times acceleration. You can deduce these units pretty quickly, right? So kilogram is mass and meter over second squared is the acceleration units of acceleration, right? But some problems we're gonna use the American system of units, and in the American system, we or the British system, I guess, we use the units of pounds. Pounds is a unit of force. Okay. Um, so this body moves from point A to point B. This distance that was traveled, or distance or the displacement, we're going to denote it by D, and the units for that is either meters or, if we're using the British system, foot. And one thing that you should pay attention, I'm introducing these things now, is if the force is in newtons, then the displacement must be in meters. You can't mix it up, right? You can't use force in newtons and then the displacement in foot. That's because the the unit of force already assumes what was the unit of length, right? So you see in newtons we're using meters here for units of length, right? So these two units play well together, and pounds play well with foot, but you can't mix them up. Right? So if force is in newtons, displacement is in meters. If force is in pounds, displacement is in foot or feet. All right. So what is the work? We're gonna try to figure out how much did this force help throughout the movement, and how much did it hinder, right? Can we measure that? Um, so we're gonna denote like this, like an absolute value, or also called a norm, the magnitude of the force, so the length of the vector, so how much the strength of this force. Um, and I'm just going to denote by F, so F without the arrow on top. It's either going to be the length of this vector, a positive number, the length of the vector, if the direction of the force agrees with the direction of the motion. So in this case that I drew, for example, F would be a positive number, right? Just the length of this vector. But if the direction of the force is opposite to that of the motion, this number here that I'm denoting by F will be a negative number, and it will be just negative the length of that vector, right? So in the case, for example, where you have a force that looks like this, right? It's against, so if our motion is from A to B, and the force is constant but against the motion, then this letter F now would be negative the length of this vector, right? So F is negative when the force is opposite to the motion, and positive when the force agrees with the direction of the motion. All right, let me erase that. Um, so using this F, then we can compute the work done by the force along the motion is just this F. So the force, the strength, basically the magnitude of the force, times the distance, right? So the stronger your force is, the more it's going to help or the more it's going to hinder. And the longer this body traveled, then the more the force helped, or the more the force hindered, right? Throughout more time, the force could help or hinder, right? So it's a pretty simple formula. It's just the force times the distance. It's how much this is basically a unit of energy, and it basically said like how much energy did you have to use to or the force kind of used or did, right? The work done, how much energy was used by this force throughout this movement. The units. So if you're using the metric system, it's just newtons times meters, force times distance. That has a name though, is denoted by J. It's a joule. It's a unit of energy. And if you're using a British system, then it's just pounds feet, right? So pounds times feet. All right, so that is the formula for the work done by a force, and it measures how much did the force help or how much did the force hinder during the motion. So let's look at an example to use this concept. This is actually kind of poorly, the phrasing is not very good. I took it straight out of the book, so I'm gonna make some comments. We need to read critically, right? So um, it says the following: how much work is done in lifting a 1.2 kilogram book off of the floor to put it on a desk that is zero point 0.7 meters high? So let me first underline the important numbers here, so we know that the book is 1.2 kilograms, right? That's how heavy it is, its mass. And the desk is 0. 0.7 meters high. And we can use that the gravitational acceleration is 9.8 meters per second squared. Right? Okay, so and on part B, we want to know how much work is done in lifting a 20-pound weight 6 feet off the floor. So they're pretty similar problems. The main difference is that in the item A, we're using the metric units, SI, and on part B, we're using the British system. Okay, so for part A, so first let me make this comment. How much work is done in lifting this book off a desk? We actually can't compute this, the work done by the lifting, unless we know how the lifting was done. It depends on how much force you applied to take this book out of the floor and onto the shelf. So the way that the book solved this problem, they make an assumption that you used a force which is equal in strength and opposite to gravity, which is definitely not the case, almost never when you're doing something like this. So a better way of saying this problem is how much work is required to lift, right, a book. That is a little bit better. However, whatever force you use, it has to be more than an equal to an opposite force to the force of gravity, right? You need to beat gravity to take this book and put it on the shelf. Um, so we can compute basically the work, that how much does gravity hinder this motion, right? So you're trying to pull this book up. Let me draw a schematic picture here. So you have a desk, something like that, right? And then you have your book here, and you want to take the book and put it on the desk. Right? So you're basically gonna, um, let me maybe write it here. So you basically want to know create a coordinate system for you. Right? So this is kind of an obvious coordinate system. Put x like this. So the floor is 0, x equals 0. And the top of the desk is 0.7 meters. That's what's given to us, right? So, and you know that gravity is going to point down all the time, so it's going to hinder this motion. Whatever you have to do, you need to beat gravity, right? So you need to do at least, so gravity is going to do negative work, right? Because it's against the motion that's going to happen. So the work required will be the positive version of that number, right? But basically, to compute this, we're going to use as force uh, the force use in your computation a force equal in strength or in magnitude, say, let's say it like that, and in the opposite direction of gravity. All right, so if you want to know what will be the force of gravity, so maybe I'll draw it over here. Gravity will point like this. Let me call this F sub g for the gravitational force, right? And F sub g without the arrow is going to be a negative number because it's pointing against the movement. Uh, and to compute the force of gravity, you can use Newton's second law, right? So force is mass times acceleration. The mass of the book is 1.2 kilos. So I'm going to use mass times acceleration, where we're going to use the gravitational acceleration, g. So it's going to be minus the mass of the book is 1.2, and gravitational acceleration is 9.8. Okay, so all right, so my calculator says that that's negative 11.76. And the units here are units of force, and we're using the metric system, so newtons. So the force that we're going to use for our problem is going to be just the opposite of that, right? So our force for our problem F is just going to be 11 positive, right? 1176 newtons. So our force is going to be equal to and in opposite direction, equal magnitude in opposite direction of the force of gravity. Okay, but constant again, same direction, right? And this is again because we're trying to compute the work required to lift the book, right? So the only thing we're computing is if you just beat gravity, how much work do you need to do, right? All right, so this is the force. The displacement here is the 0.7 meters, right? So our displacement is 0.7 in meters, and so the work required will be 11.76 times 0.7, which is equal to 8.232, and now newtons times meters, which is joules, right? So that's the work required to lift the book off the floor and put it on that shelf. Okay, so that's the answer to the problem. Now let's do part B, right? So part B, it's a very similar problem. You want to lift a 20-pound weight 6 foot off the ground, 6 feet off the ground. Right? So again, you can just draw your coordinate system like this, where x equals 0 is the floor. you have some weight. I guess I'm gonna draw it like this, some weight. All right. And you want to bring it up, right, 6 feet off the ground. This is 6. So in this case, again, we're going to use the just a force equal to and opposite. So here you have the same problem. How much work is done in lifting? It depends on how you lift this weight, right? So instead of is done in lifting the weight, you should say is required. So just read it like this every time there's some problems that have this issue with the statement. How much work is required to lift? So you just need to beat gravity, right? So we're going to use a force F, which is opposite to the force of gravity, but with the same magnitude. Okay, so in this case, though, we don't need to use the gravitational acceleration and use Newton's equation, because the pounds, when they say the weight is a 20-pound weight, it's not talking about the mass of the weight. It's actually talking already about the gravitational force, basically, that this weight is under. So pounds is already a unit of force. And in this case, we're going to take F to be equal to 20 pounds. Right, so in the gravitational force, if you want, that is acting on this weight, it points down, so it will be negative 20. But to compute how much work is required, we use F equals positive 20. And then the displacement is given to us in terms of feet, right? So 6 foot. So D is 6 feet. And so the work required to lift this weight 6 feet up in the air is just force, which is 20, times displacement, which is 6. That's just 120 pounds feet, right? There's not a name for this unit. It's a unit of energy, though. All right. So these are the examples just to illustrate the concept of work. But now what we're going to learn is what happens is if this force is actually varying with time, right? So we're going to remove, going back to the last thing we said, we're going to remove this assumption of that the force is constant, right? So if the force is not constant throughout the motion, how can we compute the work?